So, let us continue our discussion on the various aspects of design factors that we started talking in the last lecture. So, now what we are going to talk about is environment, and before I start discussing these details, there are few things that you need to really understand. Considering all the infrastructure, specifically civil engineering infrastructure, the highway pavements, be it concrete or bituminous pavement, are the most sensitive when it comes to the influence of environmental conditions. So, this includes temperature, freeze thaw index, rainfall and many other factors. The main reason is the bituminous material that you see on the surface, okay, your bituminous concrete, your dense bituminous macadam are super sensitive, hypersensitive to the influence of temperature. So, that means in a temperature range of 60 degrees centigrade, I am talking about the pavement temperature, to let us say 10 degrees centigrade, the material can go from a brittle response to ductile, whether if I can use such kind of words. So, it can be very soft and very hard. So, that means within a 24-hour time period, let us say in the month of June or 24-hour time period in the month of December, all this transition can happen, correct. So, the modulus values also will vary drastically from the afternoon to the middle of the night. It can vary orders of magnitude, and in fact, when you are presented with a lot of data, when you are doing all this design computation, you will realize how much it varies. So, when such variations are there and when your material that you are using is very sensitive to such variations, one needs to consider them. And in fact, when you are talking about let us say building construction and let us say you use an M25 concrete, you will be more worried about the influence of environmental condition, but not on the temperature. You are not going to be worried about, okay, what will be the summer temperature, what will be the winter temperature, and how the characteristic compressive strength or the modulus of elasticity of concrete will vary because of such temperature ranges. Okay, you will be talking more in terms of moisture intrusion, sulfate attack, chloride attack and all those things, but not the mechanical response that varies because of the temperature condition. But as far as your material here is concerned, you need to do that. Now, let us talk about these granular materials. So, let us say you use this as base, you use this as sub base, and for simplicity I will be talking about a subgrade. So, let us say your water table is somewhere here, and so the water can, during the rainy season, the water table can move up, in which case the modulus values of these two layers can considerably reduce. But even otherwise also what can happen, there can be seepage that can go through this, and that is why some of these layers will be designed in a specific way so that the water cannot actually go up, or in the same way you provide the drainage conditions at the surface in such a way that the water drains off completely, and then you also make this surface impervious. Okay, is that understood? So, now this also plays a very critical role. So, let us now look at each of these things one by one. So, the first thing that you are going to talk about is temperature. Freezing is not really a big issue in most of India, probably excepting Jammu and Kashmir or the Himalayan regions or the border road regions that you are going to see, and then what is really called as precipitation. So, in fact, one of your co-teachers here for this course, Dr. Nivita, when she was doing her MTech at IIT Madras, so she collected this meticulous data, air temperature data from more than 50 locations across the country, and then collected some little bit of pavement temperature data. And in fact, for many of the students, teachers who have registered for this course, In fact, one simple thing that you could do, which will not cost you a lot of money, but which will also result in good publications as well as collection of good database for the country, is to just keep recording air temperature and pavement temperature. Finding out, you can just go in front of your university or your department wherever you are working, just put some probes inside the bituminous pavement and then keep recording the temperature. And similarly, you can record the air temperature data. Air temperature data is anyway available in many websites, so it is not really a problem. Now you can establish correlations between the air temperature and the pavement temperature. Normally, roughly you can say above 0 degree centigrade. So let us say your air temperature is 35 degree centigrade or 40 degree centigrade, the pavement temperature may be around 55 to 60. Okay, when you come down below 0 degree centigrade, so the air temperature, let us say if it is 0 or -1, the pavement temperature can go little further below, -10, -15 degree centigrade it can go, right. But mostly for most of the locations in this country, we are interested in the pavement temperature in the range of, let us say 0 to or 10 to something like 70 degree centigrade. So, that is what you are going to actually see here in this country. Now, coming back to whatever I was saying, so what Dr. Nivita did was to collect this data, clean up the data. So, we collected around 40 years of air temperature data from the meteorological department Pune and then cleaned up the data. There were many places, there were gaps there. That after cleaning it up, using established air temperature, pavement temperature models, she generated the actual pavement contour for the first time in the country, and you can actually see this is your pavement contour that you see here. And of course, this has not been corrected for traffic, not corrected for speed, rate of loading and all those things. They are all subtle issues, fairly complex also, and we will not get into the details, but these are all what you can say uncorrected pavement temperature data. And you are going to see that there are some few zones here. You can see there are at least going to be 5 different zones you are going to see here. Okay. So, but the interesting part here is this particular zone, and this is where you are going to have considerably high pavement temperature. So, this is the maximum pavement temperature contour. I mean, again there are issues related to the kind of moving averages that you do and all those things, and in fact there is a publication by Dr. Nivita and I which won also an award in the Institution of Engineers proceeding. You can search for it and download it, and if you do not get it, just send an email to me or to Dr. Nivita and then we will share the paper to you. So, this is the pavement temperature contour. Similarly, this is the minimum pavement temperature contour that you are going to see. So, somewhere here. So, now this is where I live, Chennai, and you can actually see 16 to 22 degree centigrade. So, the maximum pavement temperature at Chennai can be 60 degree centigrade and the minimum can be, let us say, 16 degree centigrade. Okay, you might think, is this really that large enough? Yes, it is really large enough, and there are at least going to be 6 different regions that you are going to see. Now, why are we talking really about this? We are talking about this because the modulus values of the material that are used in this pavement regimes, pavement temperature regimes are going to substantially vary. So, if you are going to construct a road in, let us say here, and if you are going to construct a road say let us say here, you cannot expect that the same material that you use, let us say bituminous concrete grade 2, then dense bituminous macadam grade 1, then I will just restrict as of now to the bituminous layers. So, you really cannot expect that the modulus values will be identical, and which translates into whether the thickness also can be identical. So, if you are going to think that okay, the traffic level in one highway here, let us say, is the same as the traffic level here. So, all I really need to do is to adopt a uniform section, cross section across the country. It may not necessarily work. You cannot use the same VG30 grade of bitumen all across the country. So, your grade of bitumen that you are going to use is going to vary, the temperature maximum minimum temperature is going to vary, and because of this the bituminous material that you are going to provide is going to vary, the modulus is going to vary, and when the modulus is going to vary, the thickness is also going to vary. Maybe even if the traffic levels or the axial load repetitions are the same. So, just need to keep that in mind. So, with another of my student, and in fact Dr. Padma is also a co-author in the another paper, we tried to see some Rut depth simulations, we tried to do it here, and so for that what we did is to plot this kind of frequency distributions for many cities in the country. So, I am just showing you few examples. So, this is for Jaipur, this is for New Delhi, and of course, you need to understand this is the pavement temperature distribution. So, what is critical here? The critical here is this portion. The critical here similarly is this portion. This is not really a critical region, but though the number of degree days that you are going to see here is going to be more here, but two important things you need to understand: this critical temperature as well as the critical overloading that you are going to see, because the number of axles which are overloaded are going to be sufficiently small in the overall truck volume that you see there, and but nevertheless, but those small numbers added with this extremities is going to create a havoc on your pavement. Just need to keep that in mind, and I will also be able to share some of this data with you if you are interested in doing some of this analysis. So, this is for Ahmedabad, this is for Chennai. So, we try to fit a distribution. You can see what is the mean, what is the standard deviation, what is the mean, what is the standard deviation, and what is the high temperature. Now comes the most important thing that you should notice here. The mean in these are the same, but because of the variation that you are going to see, the high temperature here for a specific location, I am basically leaving lot of detailed information here, but just want to give you a flavor of it, whereas the high temperature here is going to be 54 degrees centigrade. Now, why this is important is when you are taught IRC 37, you are going to encounter a magic number. I will not give the expansion of this AAPT. When you are being taught IRC 37, you will know what that AAPT actually really means. And again we try to make some connections between the temperature as well as the Rut depth. So, if you take, let us say, 6 mm as the Rut depth, I hope you remember what exactly is rutting, the longitudinal depression in the wheel path that you are going to see, and that depth that you actually measure here. So, let us say this is your road, and let us say there is a bump that you see here. So, this is written here as 6 mm. Now, do not worry about what is written here as WMA Sassobit. This is a warm mix additive. So, we were trying to find out what is the influence of this warm mix additive as well as Rut depth is concerned, and we did lot of structural simulations, but that is not really the point. What you want to do is you want to check that there is this data related to Amritsar 14.2 mm, then you go to Jaipur 12.9 mm, and then after that you come to New Delhi, you see here that it is 8 mm, then you come to Varanasi, it is 7.2 mm, and then you go to Nagpur 6.9 mm, Ahmedabad 6.8 mm, and you will basically see how these things are varying, and of course Bhopal is 3.9 mm. So, there is a significant relation between temperature and Rut depth. Now, the point that I really want to make here the following: let us say you take 14.2 mm and 3.9 mm, and let us assume that the traffic that you see in Amritsar and the traffic that you see in Bhopal are identical. Can you provide the same cross section? You will immediately say no, because the rutting in Amritsar seems to be high. So, I should be providing a bituminous layer having more thickness, or I should be providing a bituminous layer with a better material, a stiffer material, so that the thickness can be, the rutting can be considerably reduced. So, that is the whole point of this exercise. Now, this is as far as the temperature is concerned. Now, let us come to the groundwater table. This is you can actually go from the Government of India website, you should be able to download the general groundwater table data. Okay. So, this is a picture that I just picked it up to demonstrate it to you. You can actually go find it on your own, but what is very important here is you need to understand that there are many locations in our country in which you are going to see that somewhere here, somewhere here, somewhere here, somewhere here, many places here in which you are going to see considerable the water table near the pavement. So, what does this really mean? It means that if you are having a pavement, so I can tell you roughly the construction here will be of the order of 1.2 meters. If your subgrade is decent, otherwise you can add additional 30, 40, 50 centimeters to get your compacted subgrade. So, let us say this is here, and if your water table from, let us say you measure it from here, and let us say the water table is somewhere here at 2 meters, what can happen? The water is going to slowly seep, go all the way up, and let us say the original modulus value for this was 100 MPa, it can reduce to 50 MPa. So, because of this what will happen? The load carrying capacity of this layer can reduce. So, there may be some sinking here, and when this sinks, what can happen? Each of these layers are going to sink. Individually these layers may be having the Rocade modulus property, but since you are trying to stack each layer on top of each other like a plate. So, what is the simple analogy that you can say? The strength of your chain is the strength of your weakest link. If your weakest link is here, the entire pavement will fall down. So, need to keep that in mind, but that is not how the concrete pavement actually is designed and constructed, and the analysis procedure that you use is also completely different there, right. Now, next we talk about, so we talked about traffic loading, we talked about environment. So, let us talk about the materials, and here I just need to make things little bit clear to you, so that when you negotiate the stress analysis part and when you start handling traffic and doing some design calculations, things will become very clear to you. And for those of you who have not taken our mechanical characterization of bituminous material, I suggest you to go watch at least a few of those lectures related to viscoelasticity, dynamic modulus. So, let me just write it: viscoelasticity, dynamic modulus, resilient modulus, flexural modulus, and I can keep adding more to it, stiffness modulus. So, these are various ways in which the time dependent nature of the material, bituminous material is actually measured. Now, the point is the following, and this will become clear to you as we go along. So, if this is your bituminous pavement layer, and if you are going to use elasticity theory, so call it as H1, H2, and let us call it as infinity. I am just trying to use some 3-layer theory analogy, it will become clear to you as you go along, right. So, this is going to be an elastic modulus. Now, what should we do? If it is an elastic modulus and then if your actual material is definitely not elastic, so you need to kind of use some modulus which is called in bituminous pavement engineering as surrogate modulus. So, what exactly is this surrogate modulus? Try to measure the response of the material in the manner that befits its actual nature, but reduce it in such a way that you could use within the context of the layered linear elastic theory. So, that is the whole idea. So, when one of my colleagues here will be talking about mechanical characterization, especially for within the context of picking the actual modulus value, it will become clear to you. So, I just want to only say something, the granular material is pressure dependent. So, which means, and most of you by this time will know, most of your measurements related to granular material in the geotechnical engineering laboratory would have subjected it to a confinement condition, right. So, you would have done mostly a confined test, drained or undrained is a different issue, but mostly a confinement condition, because when you subject it to confinement conditions, you mobilize the shear strength, and in real life also in the field, in the road, you are going to see the granular material confined in all the directions. So, there is going to be what is really called as a resilient modulus. As far as the bituminous materials are concerned, they are what are called as rate dependent. So, that means loading rate dependent, or to make it easier for you, if you are driving your vehicle at 20 km per hour, the response of the bituminous pavement is going to be different compared to when you are driving your vehicle at 80 km per hour. No big prices for guessing. A 20 km per hour speed vehicle will damage your pavement more than an 80 km per hour if you assume that both of them have the same axial load. Why is that? The time duration of loading in any specific area is going to be more because you are driving at a slower speed. When the time duration of loading is more, the deformation is more. When the deformation is more, the chances of failure are also going to be more. So, you are going to use something like dynamic modulus, resilient modulus within the Indian context, dynamic modulus within the MEPDG content, and something like an master curve. That is what is going to happen. Okay, but these things will be covered in detail, and in fact, I believe Dr. Nivita will be talking in terms of influence of environment on the material properties. So, let us say from the month of January to December, when there is percolation, when there is temperature change, how one should introduce all these things within the context of the modulus. So, those things will be discussed by her. Now, we come to the last design factor, and then after that we will get into the stress analysis part. So, now the failure criteria is, I am just going to go back to our IRC 37 cross section. So, need to understand. So, this is the design assumption that is made here. Okay. Please focus your attention here, because this is very important. Okay. For a moment I will remove this, I will not worry about this. Okay. Now, first we will focus our attention here, vertical strain on the subgrade. Okay. So, keep this in mind. So, this is your subgrade, granular subbase, granular base, fatigue resistance layer, rut resistance layer. You can even call it as bituminous concrete, dense bituminous macadam. I will cut all those things also, but because I want you to focus your attention only on, so let me use a different color here, two things. Now, let us go to here, right. So, what is seen here? You see there is an equation that is given here, and now as of now do not worry about this particular part. So, let us pick any of this equation. So, you see here some empirical expression is given 1.4100 times 10 power minus 8 into 1 over epsilon v to the power 4.5337. So, this is what is given here now. Now, this is your failure criteria, this is your design criteria. So, now what exactly is this? So, this is nothing but number of repetitions of a standard axial load to result rutting. Okay. So, number of repetitions of a standard axial load to result dash of rutting. So, let us write here as 10 You can have a design criteria of 20 you can have a design criteria of 5 it is up to you. In India we use 20 Americans will use 10 some other country will use 5 it all depends on country to country. Now, there are few things that I need to introduce you now and it will become clear to you as we go along. So, what exactly is this standard axial load? Concept is very simple. You go out, stand in the highway, you see different kinds of vehicles, okay, from truck, tractor trailer combination, school bus, a regular bus, everything. And in fact, it will also become very clear to you that we normally will not consider any vehicle which has a laden weight less than 3 tonnes or 4 tonnes, okay, because they do not really will cause any appreciable damage to the pavement. So, we want to do that also. So, that is fairly straightforward. Now, but we are going to see a wide spectrum of vehicles there. So, you will come back and ask, okay, so this is all fine, but how do I integrate all these things and put it in one framework? So, we are going to do some equivalence here. So, I am just going to say, and this is based on the AASHTO test. So, I am going to say, look, we are going to assume one standard axial load which will have 20 80 kilonewton. So, this is a standard axial load, and what you will do, each and every axial of different type that you are going to see in the road will be written in terms of an equivalent. So, that means if you have some other axial, you are going to say that, oh, one passage of that axial is equivalent to 1.2 times the passage of this 80 kilonewton load, that is what you are going to say. So, now you will go collect all this axial load data, do some processing, and then you will come back and say, okay, this pavement that I have designed, so let us say for 10 years, and this is based on the traffic calculations that you have done, should take 50 into 10 power 6 standard axial load repetitions. This is what you are going to say, and this comes from the traffic axial load calculations, growth rate, where your highway is located and all those things. So, this is on the left hand side, but on the right hand side what you see epsilon v. Now, what is this epsilon v? Epsilon v is nothing but the vertical compressive strain. Okay. Now, what is this vertical compressive strain? This is basically, you can actually see the way in which it has been indicated here. So, this is the vertical compressive strain. Now, you will be asking, how do I compute this vertical compressive strain? That is what we are going to see in the next few classes, and in fact, you will also be taught the use of IIT PAVE or Ken PAVE. I would prefer Ken PAVE, but since in India some of the practicing highway engineers use IIT PAVE, we will stick to IIT PAVE. Okay, right. So, now what you will be doing? you will be substituting. So, you have already designed your cross section. Now, you want to check whether that cross section can handle this kind of traffic. So, let us say you put 3000 MPa, let us say this is 40 mm, I am just giving numbers, let us say this is 2500 MPa, let us say this is 110 mm, so let us say this is 500 MPa, let us say this is 250 mm, let us say this is 200 MPa, and again this is 250 mm, and let us say this is 70 MPa, and for reasons that will become clear, we normally take it as 50 centimeter, though the depth goes infinite. So, using all these material parameters, of course, you have to assume appropriate Poisson's ratio, you will be able to compute the vertical compressive strain. Then what will you do? You will substitute it here and you will get some value here. So, now let us say if you get 60 into 10 power 6 here, okay, when you get 60 into 10 power 6, you are basically going to say I wanted 50 into 10 power 6, but the thickness that you have provided will give me 60 into 10 power 6. So, good enough for me. So, there seems to be a 1.2 factor of safety, fine. But on the other hand, if you are going to get only 40 into 10 power 6, what you are going to say? No, this is not enough for me because my axial load survey, volume count, growth rate and all my detailed calculations that I have carried out says that there are going to be 50 into 10 power 6 standard axial load repetitions, that the thickness that you have given is only 40 into 10 power 6, this is not going to be good enough for us. Wonderful. So, then what we will do? We will try to change the layer thickness, layer moduli and all those things. And there are many interesting issues related to this here, and this is what why bituminous pavement engineering becomes very interesting. Now, you can increase the thickness, you can increase the modulus. So, now you need to do some kind of a sensitivity analysis to find out what kind of layer thickness combinations, modulus combinations will result in increased resistance to rutting, but at the same time tries to reduce the cost. So, you remember the chart that we showed in the starting, wherein first you collect the input, then you do the analysis and then you pick the realistic section, that is where this comes in here. Now, one important assumption that we made here has to be stated before we move into the next section. What is the most important assumption? What you are saying is this 20 mm rutting that you mentioned is here. The strain is measured here. Then you will ask, sir, how is this possible? You measure the strain at one place, you are talking about the rutting at some other place. So, what we are assuming in bituminous pavement engineering is, we basically assume that each and every layer is stacked on top of it like this, and which is the weakest layer? The lowermost layer. If the lowermost layer, if you could limit the strain, it is assumed that all the other layers on top of it can handle things, and this is where some of these empirical factors, especially these factors, play a critical role. So, you measure the strain at one place, but you translate it into rut depth at another place, and that is why these equations are called as distress transfer functions. I hope it is clear to most of you. There are many other questions that should come up in your mind. So, are you saying that there will not be any rutting in these layers? There are going to be rutting, but we are going to ignore that. Now, we are going to ignore it within the context of IRC 37, they are not ignored in American Code of Practice. Now, let us take a look at the fatigue. and with this discussion we will bring this to a conclusion here. So, this is fatigue, and again let me cut all these things. Okay. So, now you are going to focus your attention here. Now, what exactly is this NF? NF is number of repetitions to result in let us say 20% or 10%. So, that means you take a road and say let us say this is your wheel path, this is your wheel path, and let us say there are some portions that are cracked here, there are some portions that are cracked here. You just go find out these areas, these areas, these areas, and in the overall road width, that unit length that you are looking at, if this is less than 20%, you are going to say fine. Now, come here. So, for a moment let us not worry about this factor C, that will be discussed in later. So, there is something epsilon t, and this is the resilient modulus. So, this is the resilient modulus, or whatever is the modulus that we wrote here. Now, this is epsilon t. Okay. So, this is horizontal tensile strain. Okay. Again, to answer all your questions, how do you compute horizontal tensile strain? We need to put all the modulus values, thickness, Poisson's ratio, use IIT PAVE or CanPAVE, and you can compute the strain here. Substitute it here. What is the modulus value? This is the modulus value that is given to you. So, now you are going to get some here. So, let us use the same example of 50 into 10 power 6 of axial loads, standard axial load. So, when you substitute these values, and if you get let us say 60 into 10 power 6, you are basically going to say that fine, my cross section can handle 60 into 10 power 6 before the pavement reaches this 20% cracked area. Excellent. But on the other hand, if it is 40 into 10 power 6, then we are going to have problem. Okay. Now, immediately you should be able to think, no, something is not correct here. You are measuring the strain at the bottom of the bituminous layer, and how are you relating it to the cracked area of cracked surface at the topmost layer? So, it is not seems to be not really correct, because first and foremost thing is that comes from the fracture mechanics kind of a perspective, because you are talking about cracks. Here you are using layered linear elasticity and then computing the strain. How are they going to be related? And for that we need to spend more time. So, this is where these factors play a critical role. Okay. So, this is typically the overall design process that we are going to talk about. So, let us quickly summarize the introduction, and then we will continue our next lecture on the stress analysis part. So, can you help me to summarize the introduction that we had now? Basically, we talked about different cross sections across the various countries in the world. Then after that we started talking about traffic, we talked about axle configurations, we talked about tire pressure versus contact pressure, we talked about time duration of loading, we talked about temperature, high temperature, low temperature we talked about rainfall, water table, we talked about mechanical properties, dynamic modulus, resilient modulus, we talked about failure criteria, and in fact when we were talking about the different cross section, the B1 we talked about also the design process, we talked about rutting, fatigue and all those things. So, in the next lectures we will be talking about how to compute these stresses and strains, or if you have a pavement layer like this at different locations when it is subjected to some kind of a loading, okay, what are the various stresses and strains. So, I suggest that you go back to your second year or first year strength of materials and engineering mechanics and try to revise some of the Rocade terminology, because if I use principal stresses, you should know what it means. I will provide you with the Rocade material. I will also share some of the locations wherein you can read more about this material, but on your own interest please try and understand. For instance, you should be able to clearly differentiate between isotropy, inhomogeneity, stress functions. So, while I will be very keen on addressing, deriving all this from the first principle, we actually do not the focus of this course is not in that. In fact, at IIT Madras when I teach this course, I have been teaching this analysis and design of pavements from 2004 or 5. So, depending on the interest of the students, so we have special Saturday lectures in which we get into the solid mechanics part of it, because somebody would want to know, okay, how did you pick this stress function? So, then we tell them about Airy's stress function and so on and so forth, but that is something that I will not do here. If you are very keen on doing it, we will do it later, but at some appropriate venue. Thank you so much.